As we start looking at applications of integration, we'll start with a familiar one with the area under a curve, and we're going to extend that slightly to the area between two curves, between two functions. And you may have seen some of this in Calc 1, so this may be review to some extent, but hopefully we'll see a few extra things here as well. Let me start with a really simple example where we're just going to look for the area beneath one function. So let's say we take the function y equals x cubed on the interval from 1 to 3. And this is kind of where you started in Calc 1, looking at definite integrals by finding the area underneath the curve. We'll draw a picture. It's always a good idea to draw a picture for one of these. And this picture looks something like this. There's the function y equals x cubed, and our limits of integration are from 1 to 3. So we can enclose this area, and what we're looking for is the area that's shaded there. Now we know how to do this. This is the definite integral from 1 to 3 of x cubed dx. And if you remember, you started back in Calc 1 by looking at this, and you divided this area into small vertical rectangles, one of which I'm shown here. And the width of the rectangle was delta x. The height of the rectangle was determined by the function x cubed. And then when you sum these together and you let the thickness of the rectangle get vanishingly small, you end up with this limit that leads to this definite integral. So that's all the familiar stuff. Integrating this is fairly straightforward, as most of the integrals will be when we do these applications. We won't have very complicated integrals most of the time. This is just 1/4 x to the 4th, evaluated from 1 to 3. So that would be 1/4 times 3 to the 4th, which is 81, minus 1/4 times 1 to the 4th. And this turns out to equal 20. We won't spend a lot of time doing the arithmetic there. So this is very familiar. This is already something that you are comfortable with. And when we want to extend this to the area between two curves, I'll just point out that we actually did find the area between two curves here. When we said the area beneath y equals x cubed, really what we meant was the area between y equals x cubed and the x-axis, y equals 0. So really, we built two functions here, one at y equals 0 and one at y equals x cubed, and we found the area between them. So we've actually done this before, and it's just a different way of looking at it. But now if we make a different function be our lower function, let's see what happens. So for example, let's say we want the area between y equals x squared and y equals x. Now notice the difference between the two problems. First of all, now we're saying the area between two curves, but also notice that before we were given a specific interval where we're looking for the area. In other words, we were given right and left bounds to our box that we were drawing in, and that gave us these boundaries on the right and the left. This time we're not given the boundaries on the right and the left. We have to think about how to handle that separately. As you go through this section and you do homework examples and other problems on this, you could be given limits of integration, you could be given a left and a right bound, or you could not be given those bounds. And so you have to know what to do in either case. So since we're not given an interval, there must be a natural interval to use. In other words, there must be bounds that we can figure out based on the picture. So we should really draw a picture to see what's going on here. If we draw y equals x squared, that would look something like this. It's parabola. And then y equals x would look more or less like this. Now that we've drawn the picture, you should be able to interpret what we mean when we say the area between these curves, meaning the area fully bounded by them. So we need to have a closed, bounded area to do this problem. We can't have an open-ended thing. So we can't use this area up here because that's open-ended and it's just going to continue to grow. and the same thing on the left side. But in between, there's this enclosed area bounded by these two functions. So what we're looking for is this shaded region right here, which means we need to figure out what our bounds of integration are based on what the left and right endpoint of this area is. In other words, we're looking for the values where these two functions cross each other. Now for y equals x squared and y equals x, it's pretty easy. You might be able to just interpret the answer and figure out from the picture what those values are. But if you can't do that so easily, let me show you in general how to do this. You would set the two functions equal to each other and then solve this for x. Now I should caution you, when I write this down, you may be tempted to say, to solve for x, let's just divide both sides by x, which is a place to start, but if you just do that, you will miss something. Because when you divide both sides by x, you're assuming that x is not 0, because we're not allowed to divide by 0. So the moment you say, let's divide both sides by x, you're saying, let me ignore the possibility that x is 0 and proceed from there. So if you do that, you'll figure out x equals 1 is one of your answers, but you'll miss the possibility that x could be 0. So if you're really careful, you could say, okay, let's assume for a minute x is not 0, divide both sides by x, we get 1, and then let me check and see if 0 is the other answer. And in this case it is. But that's a little bit messy and a little bit prone to error. So let's find a better way to do this. A better way to do this is to subtract x on both sides and set up this quadratic equation, which you can solve in this case by factoring. You can factor out an x. And now we're not missing any answers. Now we see the two answers are x equals 0 and x equals 1 based on that quadratic equation. Of course, you could also use the quadratic formula or any other method that applies. So that's a little bit safer. If you set them equal to each other and then noticing that it's quadratic, you move everything to one side and either factor or apply the quadratic formula, etc. But however you do it, we get the bounds of integration are 0 and 1, the 2 points where they cross. Now we'll see an example a little bit later that might be a little bit different. Let's say, pausing this one for a second, let's say our two functions looked like this. And now if we were asked to find the area between the two functions, we would need to find both of these areas. So in that case, we'd have to figure out the three values where they cross. We'll get to those later on, but it may be that your functions cross more than twice, and that's why it's always important to draw a picture at the beginning so you have a sense of the overall structure of the problem and you can predict how much you need to look for and how complicated it's going to be. So we'll set that one aside for now and return to our problem here. So if we want the area between two curves, looking back at what we did earlier, where we found the area beneath one function, we can use that to apply to this one. So if I want the area between them, what we can do is we can find the area under the upper function. So in our case, the upper function is the straight line y equals x. If we found that full area, and then we found the area underneath the lower function, in our case that's y equals x squared. Notice that it's underneath on the range that we're interested in, from 0 to 1. If we found the area underneath there, and removed that from our earlier area, if we found the area under the upper one and then subtracted the area under the lower one, what would remain would be the shaded region that we're really looking for. So to calculate the area between the two functions, we can calculate the area under the upper function, which would be the integral from 0 to 1 of x dx, and then subtract off the area under the lower function, which is the integral of x squared dx from 0 to 1. And again, when we use the term upper and lower function here, we mean the upper function and the lower function on the interval that we're interested in, from 0 to 1. Past 1, x squared is above x, and then below 0, the same thing. Now notice that we can combine these two into one integral, so we'll often write instead a single integral of x minus x squared, or whatever functions we're using. I'll wrap this one up really quick. It's an easy integral to do. You get 1/2 x squared minus 1/3 x cubed, evaluated from 0 to 1. And skipping a little bit of arithmetic, you should get 1/6 as the answer. As with all of these application problems, the key is in the setup. The setup is the hard part, and then actually carrying out the integral is not very difficult and not very interesting. Now notice, comparing this to the one we did earlier, the area underneath y equals x cubed, really we could have set that first one up in the same way, where we have the area underneath y equals x cubed minus the area underneath 0, which is nothing. And so when you subtract off 0, you get the same answer that we started with. So really, every time we were doing the area beneath a function, we were really doing the area between that function and y equals 0. And we can see that now here. And the more general version is that the area between two curves is the integral of the upper minus the lower. So we can write that down in sort of general terms, that the integral of the upper function minus the lower function gives us the area between them. And when we say upper and lower, of course we mean the one that's further away from y equals 0 and the one that's closer to y equals 0, which might sound like a really simple point, but I make that point because later on we're going to do ones where we turn things sideways, and instead of using upper and lower in that case, we might use the terms larger and smaller, or the one further to the right and further to the left. So keep that in mind as we go forward to that. And this formula, quote unquote, here really applies no matter where your functions are. It intuitively makes sense when both of them are above the x-axis, when they're both positive. But it turns out that even if we were to draw a different picture, where one of them is above and one of them is below. So let's say we have something like this, where we draw one function like this and another function like this. Let's say this is f of x and this is g of x. If you want to find the area between those two, we're looking for this area here combined with this area here underneath the x-axis. And so you might look at this and say, well, we're really going to be adding two areas together because we have one area above the x-axis combined with an area below, and really starting with two separate pieces and adding them together. But if you think carefully about this, the area in blue underneath f of x is going to be the integral, let's call these limits a and b, the integral from a to b of f of x. The area underneath the x-axis, the area shaded in red there, will be related to the integral of g of x. But if you think about it, when you calculate the integral of g of x, is the answer going to be positive or negative? Since that area is below the x-axis, it's going to be negative. And back in Calc 1 and up to this point, when we've talked about the area under a curve, we allowed for the possibility of negative areas, just as a way of keeping track of whether the area was above or below the x-axis. When we start using the term the area between two functions, we're going to go back to that sense of area as being a positive value only. So we're going to think about just positive areas. So really the area underneath the x-axis, if we want the positive version of that, we would need to make this negative. Because when we calculate the integral, we'll get a negative number. So the opposite of that would be the positive area. So when you add those two together, it really turns into the integral of f of x minus g of x again. So even if one is above and one is below, the formula of upper minus lower still works because we've counted areas below as negative. So everything's consistent and it all works together. In fact, you could think about a picture also where both functions are negative, like this. And you should try thinking about this on your own and see if you can apply the same kind of logic and see how this same formula still applies. But it does. The upper function minus the lower still gives you the correct positive answer for the area between the two curves.